So the topic of today, good evening, good morning. It's Shaketune versus Klipper. We're going to be comparing. I know it says between the input shapers, but we're going to be comparing and taking a look at how Shaketune's results compare to Klipper's results and what we can learn from this. And which one should we be using and why? Kind of just overall, why should we use one over the other? So today, the test printer is my V2.4. It's a 350. Serial is 3812. Very beautiful, as you can see. I chose this one because it's a heated chamber, so that heat will have some effect on the parts moving and whatever. So there's going to be a printing aspect to this, where I'm going to show you what the prints actually look like at different uh, resonance testing parameters. So this printer is modded. It's got the Stealth burner, the Fly SB 2040, the V1 of Rapido, CHT umbilical. I'm using the IGUS cable. It's a very heavy cable, so it's harder to get good resonance, because it always seems to want to screw it up, especially in Y. If you're going to do this, I would either recommend if you want a pre-made cable, either a 3DO cable. It's a lighter, it's more flexible, or make your own with 4 wires in a sleeve of some sort. That would probably be a better approach than the IGUS cable. The IGUS cable really is made to go into cable chains, so that's what it's primary why it was designed for. The 3DO is more of like a USB style cable. I mean, it looks like USB. It's flexible like that too. It's not a USB, but it looks like it. So if you just have a regular CAN bus setup, I'd go with the 3DO 4-wire cable. It has Rama idlers, the pin mod. I have if we go back here, I added this Hark umbilical pass through. I still have, you can maybe see it here. Let's see if we can blow this up a bit. I still have the galvanic Bowden thing there. Um, I did have to route it through that and then zip tie the CAN bus cable to that to help out with my resonance. I don't think the PG7 connector offers enough support to the CAN bus cable. So something underneath, if a mod could come out with a piece of plastic that would kind of direct it this way, and we could zip tie to that piece of plastic, I think that would be better than this PG7. Um, but as it is, the way I know this picture doesn't show up, but I did zip tie everything to the galvanic Bowden thingamajig. Uh, so we have the Nevermore. I got two of them, left and right. Um, I had to redo this whole setup because, you know, this is my first Voron, and building my first Voron, I used Super Lube with the PTFE things in it, and I took this apart because I broke my extruder or some plastic on it, so I decided it was time to re-lube all the linear rails, and my X rail was shot. As soon as I cleaned it, the dust, the dirt, and grime was what was making it work really good. As soon as I cleaned it out, yeah. So I replaced that, and I decided while replacing my X linear rail to go ahead and kind of clean things up in here. I vacuumed it. It used to have a lot more plastic inside. So I also have the Mandela Rose Works build plate with magnets. I love this thing. Yeah, you can't use a beacon or cartographer on it, but I'm using tap, so it's fine. I also got their kinematic kit. I have TI backers on X and Y, and this one's running flex tap. And I just made a video about running the flex tap for 100 hours and only really needed to adjust it once. Uh, so that's what this is using. This is where I'm testing that out on. All right, so what's the difference between Klipper and Shaketune? Klipper uses a default damping ratio of 0.1. That's the biggest difference here in the calculation of the shapers. Whereas Shaketune, they calculate the damping ratio from the measured graph. It's an approximation of damping ratio, but it's a better approximation than just using a flat 0.1 in the calculation of your damping ratio. Both tests use the built-in test resonance macro, and that resonance macro really is all it does is excite the tool head and collect the data. So it doesn't do any of the math behind the data to give you your shapers. So they both use that. So as I stated, the biggest difference is going to be how these shaper values are calculated. This whole thing led me down a rabbit hole because, as we'll see later, I was getting graphs that look exactly alike, with really, well, 90% exactly alike, where the only major difference was the damping ratio. And I'm like, well, what does that have to do? Like, why is that such a big deal? So if you bear with me, it's going to be a long video. I'll go out through some of the math and I'll show you some examples I made in an Excel sheet so that we can kind of pop in different examples and see how that actually matters. The damping ratio actually matters. So belt shaper, it's basically in Shaketune you're going to run belt shaper. In Klipper you're going to go through all three of these commands. So you're going to do the test resonance. The 1 I believe is the A axis. The 1 -1 is the B axis. Then you're going to run this SSH, and the files are going to be in temp. It's a 4-step process versus a 2-step process. So the first thing we're going to look at is belt shaper with FlexTap. Belt shaper is going to be exactly the same. So there is no difference because there is no real math going on to display the graphs. The extra math comes in Klipper, where he's doing a peak, searching for peaks. Any peak that's basically over this green zone, this one is too close. But these two here, he's going to look for all the peaks and try to match them up. So it gives you this extra delta stuff, and then the spectrogram, which is good for finding vertical lines, and we discussed that in my in the other video about belt shaper and Shaketune. So they both perform the same. They both do the same job here. The only thing is you get a little extra information with Shaketune. Input shaper, very similar. In Shaketune, you're going to run the axis shaper calibration, which is basically input shaper, and the files in the main cell config. Klipper, you have 4 more steps or 5 steps if you want to count this to get it. These are the commands. They're all these are in measure resonance right here in the Klipper Klipper website. So this is what our data looks like. Same runs. So this is run. I ran Klipper. All the Shaketune graphs were run first. Then all the Klipper graphs were run next. And there is always going to be a run-to-run variation. It may be small. It may be a little larger. So they're not ever going to look exactly alike. They'll be really damn close, but never exactly alike. So what do we see here? If we compare it, you guys can't see this one at all. Let me try and blow this one up, see if we can get a better view. We'll get rid of that spectrogram for now. We can kind of shrink this one. Just blow this guy up. Okay. Well, now we're cutting data off. Is that okay? Yeah, you can probably see that. So our frequency here, MZV, 55.4 versus 54.6. Okay, so they're about the same. They're reporting about the same, although Shaketune is telling you you're going to have 0.4% vibrations left over, and then Klipper's saying 0. And then EI is giving us 67.2 and 67. Like they're really, they're only 0.2 hertz away from each other in both MZV and X. But the vibrations are different, right? So this is the MZV vibrations, and then we look at accels. And we can see that this accel is 200 less than Shaketune. However, EI is 100 less. So for all intents and purposes, these graphs are exactly the same. And the only difference is, really the real difference is this damping ratio. how Shaketune calculates damping ratio. It's 0.65, and this is always, Klipper always defaults to 0.1. So then we look at Y. And yeah, this is not great. I gotta fix that. Um, so here we have a very similar situation where the graphs all look the same, right? We get MZV's giving us 37. We're getting 37.4 in Klipper. We're getting 45 for EI, and we're getting 44.8 for EI and Klipper. The smoothing is the same on both of these. This is showing 0.2 vibration on MZV. This is showing 0. We have 4,000 Excel here, 41 over here, and the 37's the same. Once again, the major difference here is the damping ratio. And I talked to Fricks about this, and the vibrations here, for vibrations, generally, he says if you've got less than 5% vibration on a graph, that it's okay to print. You do run a test print, obviously, but if you're less than 5%, you're probably pretty good. So for all intents and purposes, the Y shapers are the same, except for the damping ratio, right? 0.69 to 0.1. And we're going to look and see, I think if I can pull that up. So let me see where I put it. I should be more prepared. Alright, so, that's the wrong one. That's my flow calculation, which we might get into too. So, let me find my Klipper. Okay, so if you guys go to Shaper Defs, it's in Clippy, on Klipper GitHub. You go to Clippy Extras Shaper Defs. You will see all the maths that they have for calculating the different shapers. And so these back here are the shapers. All the dashed lines in the back that you see, those are the shapers that we're calculating. And these get put into the motor at different pulses and different times. So different amplitude pulses and different times. And I was talking to Andrew McGurr about this and kind of cleared up actually how this works for the motors. So the first thing they do is they take we'll get to them. Let's do the math. So this is not going to be the best explanation, guys, but it's going to kind of helpfully get you in the right path. So, if we look at something like ZV is real easy, right? You've got to calculate this DF, K, and TD parameter first, right? And the DF and K rely on the damping ratio as part of their math. Well, what do the DF, K, and TD have to do with this? The shapers all the shapers in Klipper will return an amplitude value in A and a time value in T. The amplitude, you have two points. You'll have an amplitude of 1 for ZV, and then your K value, which is this calculated value. And then you have a time or T value of 0, always 0, and then this 5 times TD, which is basically 1 over your shaper times DF, the shaper frequency. So that's that main, let's go back there. That's this main frequency here. This is part of your DF calculation. And then, let me bouncing back and forth, guys. This DF has to do with your damping ratio. So we can start seeing that this damping ratio, if we change this value, we're going to affect both the amplitude and the time. I believe it's amplitude and time. I know someone's going to correct me, and please do. Of your pulse for the shaper. And every single one of these, right? So if you look at ZV, they have a ZVD. It's not used because this is the frequency, the shaper frequency has a real big part of this. And if you're not exact, it can throw it off. So they use MZV instead. MZV has 3 points. So it has 3 amplitudes and 3 times. And these pulses come at different times during the movement of the motors. So if you say, I want, let me see if I can explain this. And I hope I get it right. I'm sure someone will correct me. Please do. I got a motor pulse, right? So I'm going to tell the motor. Let me get a proper motor pulse here. So say I got a motor pulse like this, right? This is going to come from my TMC drivers, right? What the shaper is going to do, and it's going to do some sort of acceleration. It's going to, where did my mouse go? It's going to put in some pulses like this to counteract the acceleration the tool head, or the resonance the tool head is experiencing. So, and it does a whole bunch more, and I know I'm not doing it credit, but I'm just trying to give you guys an idea of how the damping ratio matters and what it does, right? So from our Klipper equations, from our shaper equations, let's take a look at ZV because it's the easiest. Our first amplitude is always going to be 1, and these are convolved with the movement of the motors, I believe. So it all gets calculated back in, oh good God, another thing here, but basically it's going to send 2 pulses, one of an amplitude 1, one of an amplitude k at a time 0, and then a time 5 times TD. So this is going to let the original signal through, then this is going to modify the original signal at a different time period by this mount, right? Okay. What does this look like? So I calculated all these values here, right? So let's say we have this frequency here. We'll get to the rest. So this is, let's go all the way. So this is when your damping ratios are far off, right? So if we have a damping ratio from Klipper of this, and a frequency damping ratio, these are going to be the pulses that it's going to send into. These are actually the shaper values that's going to send into the motion system to get rid of our resonance. And we can see that the damping ratios, the main peaks are fairly similar, right? 51.4, they're fairly close. The biggest difference is damping ratios. And the first numbers, basically because it's 1 here, on this one, it's going to be the same. But if you look, can we do this side by side? This is, let's see here. So if you got the math on one side and you got this on the other side. Okay, so what values, there we go. So for something like ZV, this 1 and K, this is 1, this is our K value, our calculated K value using this. And then this is 0 and half of our TD. All right. The big thing I think comes down to the difference. So if we have the same frequency on all the shapers, right? So if you look here, I got the same frequency here, the same frequency here. But my damping ratios are different. Right? So if I put, well, we have that 0.065, right? It's going to change all of our shaper values for A and T. And you can see here, I did deltas down here. So it's the difference between this value and this value. So how much different is the bottom value? We can see that even though if we make them the same, right, there's no difference. But if we do something like 6.5, like one of my graphs showed, you can see that, see if I get rid of ZVD, but if we look at MZ, we see there's a big difference here. And we're not talking big difference, we're not talking like 5, 10, right? Like this is 0.27. All right, that's the difference in 1A. The other A is 0.15 for MZV, and then we have 0.0025, 0.005 for our time periods, right? But when you think about it, what we're trying to do is we're trying to cancel out all the resonance in the motion system for that period of time, for that movement of the tool head. And so I'm sure you guys have run it where Klipper says 0 and you still have resonance. Well, that's because Klipper is guessing at this damping rate. It's taking an educated guess and saying 0.1 is going to work for most people most of the time. But if you can get these things tuned, like you can get a Voron tuned down to like 0.55 on your damping ratio. And what is the damping ratio? That's another good question. It's basically calculated from here, from the square root of, I believe it's square root of 2, or it's square root of 2 over 2. It's 2, or what, we'll just say, we'll do it this way. Oh, go back. It is the peak times, I believe, so it's peak times 0.707, right? You find that value in your graph, and then you put a line across it. It's going to be, and there's some math around it, but it's basically these points here, whatever that point is, with some math, and it gives you the width, effectively, gives you the width of the peak, right? So we know we have the center point, we know the center point of the peak, or the center point of the shaper, which is here, right? And then we know where the peak is, the 0.707 of the peak. So from this, we can basically reconstruct the graph. And that's what the damping ratio is. And another way to look at it, it is how much does this thing ring, right? How does it ride? Does it ring like that? Does it ring like this, right? Does it ring like this? All right, it's how close does this thing go to steady state? How much is it going like this? And that's basically what it is, and this is how we are going to calculate it. Now, let me pull this thing back up. So what this is, by changing the damping ratio, we have now changed the A component of our shaper, and we've changed the T component. Different amplitudes, different times. And this will affect how we've moved the motion of the tool head to cancel out the resonance. Long story long. So if you can get a more accurate damping ratio, you can get a more accurate shaper, and therefore get a more accurate shaper and its A and T values. You want the A values and the T values because that's what Klipper uses. So more accurate damping ratio, more accurate resonance cancellation. Now, does it matter? Right? I mean, it always goes down to the question, does it matter? In some sense, no. Right? In some sense, Klipper's 0.1 will do just fine. I got some prints I'm going to show you later. Looks just fine. No problems. In other situations, yes. The thing is, this is a free kind of tuning, right? It doesn't cost anything for Shaketune, and this is the value you want. You want the more accurate damping ratio, so why not take it? I mean, you don't have to, right? You're going to get good prints if you can get this thing down to 0. You're going to get good prints, but can you push the machine as far as you want? Still get good prints. So this took me down another rabbit hole. So I decided to test this out, right? I'm like, okay, well, I'm always talking about how you want to do this, so let's do some prints. So I did some prints. Use Prusa Slicer 2.72. I changed my acceleration for my external and internal parameters. That's all I changed. Everything else was the same based upon the recommended maximum thing here. I'll give you more as I did it, but that's what I changed. Square corner velocity is at 5. On my filament settings, I'm using KVP. It's the last bit of my orange roll. Um, I turned off auto cooling. I know I have it set here, but I turned it off. I didn't want auto cooling on at all. 2.4. My line width, this is what I used. I had the chamber preheated to 45°C for 30. Took 37 minutes to preheat. During the prints of all the different prints, my chamber temp was over around 57°C for all the prints. So maybe the first one was a little low, but the rest were all the same. 0.2 layer height, and then my perimeters, as you can see. So this is my ADXL settings. When I would do the print, this is what I use for Shaketune using MZV, Shaketune using EI, and Klipper using MZV. Klipper, I disabled damping ratio because it defaults to 0.1. So I didn't want the damping ratios of the Shaketune to mess with that. And then for speeds, I basically chose my speeds using the vibration measurement as I've talked about in the past. So let me show you what the initial ones are. And then after that, what I did is I decided to push it. I decided, I'm pretty conservative in my prints and my speeds because I want to get the best prints possible. But I said, hell, we're doing this, so let's push it. Give me a second. I'll be right back because I got to set up for the prints to show you that, and then we'll talk about it more. Okay, so this is Cube 1, which was done with the Shaketune MZV. Oh, let's get over. Where's my mouse? This right here. Oh, let's get rid of that. Done with the MZV. So we got. Well, let's see if I can find this. 1, 2, and 3. So this is Cube 1, and what we can see is I don't know if you guys can see it. There's that little thing right here. But that's more of a pressure advance coming off the corner. So sometimes it'll come off the corner right, and then it'll kind of get a rounded area there, and then down. So that's like EM and PA right there. If we look at the Y, let's see if I can't. Okay. You don't see any ringing on the Y there. And then the X, no ringing there either. The X, so right here on the X, let's see if we can, you might be able to see it, and it's like right about here. That is also going to be a pressure advance on the X, but what we're looking for is it kind of, let me see if I got a pen here. So we're looking for something like this, right on the X. And what we have here, right here, is just the standard PA, because when you, let's do on the bottom. When you come and do PA, if you come around a corner like this, let's call this the corner, it's going to come in and do one of those things, right? Because it's speeding up, slowing down, it's going to take off. And because it's taking off, it's going to leave just a little bit less filament there. So you might get one of these things. You can fix that by readjusting your PA and potentially your extrusion multiplier. So that's what we're seeing, and we can see that here on the X. Or I can. This is so hard to do. I know why people perfect lighting with this stuff. There we go. Better. Okay, so right there, it's going to be right there. But once again, we're not seeing anything like this on the Y coming off. Here, you're going to see, I think you guys can see it, it's the same thing. So it's the same that happens over here that happens over here. That's a PA thing. This is right here, that's a seam. So that is going to be your retract and de-retract setting. I'm not even seeing VFAs on this. So VFAs, if you saw them, they would be lines that come down like this. That's what a VFA would look like. And VFA, most common one is your belts. You could also get motor induced, which is um, why we run this test is vibrations. So we're trying to stay away from the motor vibrations. But if you see them, they're going to be oops, who am I? The motor vibrations are generally going to be really faint, and they might be even closer than 2 millimeters. If it's 2 millimeters, it's going to be your belt. So here, right, you can see this right here, right there. That is not resonance. That is, once again, PA and EM, most likely PA. And so Cube 1 looked good. Was happy with it. So to remind us, Cube 2, let's pull that up. We're doing EI. Now, the reason we did EI, if we go back up here, we got a bunch of junk here, but the reason we did EI is because on X, we had vibrations, right? We had MZV vibrations, so I said, why not just run a EI vibration test? All right, let's just throw another one. Why not? It's just another print. So that's why we're doing EI on both of these to see how that compared to MZV. So if we look here, let's get the right distance. Can we get that distance? This is going to be like half the... Okay. You can see here, that's pretty clean. By going to EI on this one, I lose a little acceleration, max acceleration, and I lose or gain some smoothing. Now this one's really weird. This Y, when I went to EI, I started to get this here. And this. This is EI on Y. Not sure what that is. That's not really resonance. It's not going to come at an angle like that, especially like that. So it might have been something else going on, but it's got, that's the PA thing here, but nothing really else. So I don't know what this is. I don't know what that is. On the other Y side, we don't really have it. I think you guys can see this. I can barely see this, but we got these right here. But that's, that. And then there's right there. So it looks like for this test, MZV actually did better. This is the X side, the back of the X side. So that's number 2. So number 3 is the Klipper MZV. Very similar to this. Once again, the only difference is the damping ratio. So number 3, we'll start with the Y side. Okay, I think you guys can see it. Now we're getting a little bit more. So, excuse me. Based on the acceleration I set from it, this might be causing this stuff here. Okay, can I get a better view? There we go. Right here. Let's see if I can, right there and right there. That could come from the acceleration and once again the pressure advance, because I didn't tune these things for the increase in acceleration. My previous acceleration was like 1,000. So we went from 1,000 to whatever Klipper said, and I didn't retune any of my pressure advances, nothing. The only value I changed. But we're not seeing, once again, we're not seeing resonance on the Y here. What are we getting over here? Nothing really. See the Y? If we're getting that weird kind of thing here. And here, but not really. Seeing anything. X looks pretty good. So, if I look at all three cubes, 1, 2, and 3. Right, 1, 2, and 3. I would say that the MZV on Klipper and the MZV on Shaketune did about the same. And if you remember, the Shaketune had 0.4 resonance. So performance-wise, at my speeds that I'm running this thing at, they appear to visually print the same. So I said, why not? I said, okay, great, let's push it. And I said, okay, based on this, my only increase, so let's push it. I increased Excel 4K on Shaketune, which you guys saw. And then I said, how fast can we go? How good can the Shaketune MZV go? I only tested MZV on Shaketune, which is, as we saw, very similar to Klipper. Once again, only difference is the damping ratio. So I said let's start doing it. So I did a whole bunch of tests here. Right, I got a 6 test I also did. The second test, I increased the internal external perimeter to 250. Increased my so I kept my external perimeter speed at 4,000 this whole time. I did not increase it, but I increased everything else because my goal is quality. So I know at 4K external, it prints good. External acceleration. So I just started, let's start messing with the rest of the settings. So the first one is the internal external at 250. Internal perimeter speed to 6,000. This is what I got. So this is number 2. This is what I got. That looked good to me. I'm not seeing any major issues. So I said, let's do number 3. Number 3. Let's increase my max flow from 24 to 30. If you recall, this is a Rapido CH with the CHT 0.4 CHT nozzle. So I increased my external perimeter speed to 350, my internal perimeter speed to 325. The reason that I didn't increase them the exact same is I'm basically maxing out my flow rate for what I set it for. So I set it to 30 based upon my line width, my layer height. At 350, I am close to or maxing out this 30 volumetric speed flow. So my internals are wider than my externals, I believe, or maybe I screwed this up and let's see here. That's not the graph. That's the one. So you can see here my externals are 40. So I should have flipped the speeds. All right, lesson learned. These speeds should be flipped, but that's okay. It's okay. We did the test. This is what we got. I really wish Prusa Slicer would call perimeters external perimeters. Just calling it perimeters, I always want to think it's just our internal perimeter. Internal perimeters, they should relabel it internal perimeters instead of perimeters. It just screws me up all the time in my brain. So this is why those new settings. Oh, can we get this? Okay. And I don't print tops on these because I'm really just looking at the perimeters. I did print tops when we get to starting with number 4. So that looked good. So I said, let's keep going. So we increased the max flow rate to 350. I think I fixed my internal speeds at this one. So we're 375, 390. Infill is so low because I do double infills. So it will max out my hot end faster than a single line width. And I'm probably doing the math wrong there too, guys. but 155 is what I calculated to be my max. I increased everything here, as you can see. This is our cube. So, oh, this is the top. So this is number 4. I got some EM issues. Let's get this up here. Some EM issues there. But other than that, I mean, it's still smooth, still feels good. You can just see some. I don't know if you guys. There you go. That's a good picture. You can still kind of see that. It's not PIF quality, but it's good enough for me. So that's X side. This is the Y. Just trying to make sure you guys can see all the potential defects in it. This is not the, let's only show the pretty side. Let's show it all, because we need to know what's realistic here. Alright, so that's a good example of that PA starting thing. You can see that real good there. But that looked good. That looked good. So then I said, okay, number 5, I'm printing cubes here. What do other things look like? And I increased the speed. Oh, I did more than 4. Hang on. Was that 4? That is 4. Okay, so another thing. Forgot about this guy. So this, I will leave a link to this. This is called the Stealthvase by John. This is really good if you want to see your vibrations on different axes, because it basically, let me give you an example here. I printed this guy. I added the letter X and the letter Y in Prusa Slicer, just one of their embossing thing, so I knew what I was looking at. But it will give you all these different angles from which to see. So you can look at your print and you can see where your troublesome angles are. And you'll just get either VFAs, you'll get, generally it'll happen on, sometimes it'll happen on the angles, it'll happen on off angles. So this one right here, it's got an issue right there. I don't know if you guys can see it. I can see it. Can you even see it? Not really. It's got a rippling effect, so it's kind of got these lines going like this. There's my seam, probably need to fix that. But other than that, there's no real issues. This right here is all sunken in because it's doing a sharp, it's turning in. It's all angles. What's really nice about this is that as a vibration calibration or vibration kind of visualization test, is you get a place to put all your stuff. So you can just drop your screws in there, and these things are great. So there's test, and it's a useful test. So that's number 4. The biggest issue I'm starting to see is with so this is solid infill. This isn't top solid infill because of the way this model is done. This is just regular solid infill. And you can start to see some of the gapping, right? So right here, you can start seeing the EM issues develop, right? Because I'm not flowing enough filament there, and this is because I'm increasing the speed. So then that took us to number 5. I went from speed flow of 35 to 40, jacked up my speeds, my infill is about the same. Is it about the same? Nope. Increase the infill, increase the solid infill, which is what that issue I just saw, and then I increased. I said, let's go with 7,000 external perimeter cell. So I increased my externals. So my internals were already at 6,000. Oh, I think I screwed this one up again. But either way, I increased that. And I said, okay, can the slicer handle it? Travel with 10K, all this stuff. And then I decided to print them. So I printed a benchy. Got to see what it looks like, and then printed number 5. So number 5, okay, let's see. Can we see this? There we go. I mean, that's pretty good. Let's see, can we get the top? I mean, the top's pretty good. You can definitely see EM.
So this one, the reason this is here, I had a my filament sensor went off, and this is the extra little goop left over from that filament sensor. But this was not a anything else, just filament sensor went off, and then it came back in and did that. So that's that side. So that looked pretty good. Then I did a benchy, and I realized, so there's a difference in this, right? These two. This is more of a structural element, lots of squares, kind of sharper angles. This has got that organic aspect to it, right? It's got this hole, it's got an overhang. The overhangs here are de minimis, right? You're really talking the overhangs in a Voron cube. You're like there. You're like down here in your bridging area here. But Benchy's got this kind of overhang. You know, you can see that this is, the seam is not great. That's the bottom. But all in all, besides this, and this could be cool. This is cooling issue. This is right here. Let's see if I can. Come on. So this right here is a cooling issue. So I will increase the fan, or I did. But the smokestack, you can see more cooling, and then the top. But there's okay at 7,000 Excel, so it's over what Klipper recommends, or both Klipper and Shaketune recommend. There is very, very slight ghosting right here. There's none on this side. There's nothing there. But on this one, right there. So we went back to the drawing board. And said, okay, this is what I settle for. Because I started running this and I started getting skipping steps. And I think my travel was too fast at 10K, at 400. For my system, my travel was too fast. So I brought everything down, right? I think I was doing a bunch of tests. Where's my mouse go? Alright, I was doing a bunch of tests at 250 and 125. I settled out 250. So this is my new parameters. This is everything I'm kind of selling for. I did increase EM from 0.94 to 9.5. I did increase the fan speed to 80. This is stealth burner, so it's okay because it's fine. I left all my accels at 4,000. I didn't want any more skipping. I think it's skipping because of the acceleration. Left travel at 6,000. This is fine. It didn't really save much time for me. And I decided to print all three at once because I wanted to see if I have skipping issues, layer shifting, whatever, if I printed 3 models instead of just one, right? More realistic test. So this was my Stealthvase. You can kind of still see that there's still some there. But then again, it's top solid infill. It's not top layer. So the top layers you'll see come out fine, are good enough. There is no real vibrations on this thing. That right there, that's because it's shifting to 2 different angles, or actually 3 right there. You'll see it on always see it on one of mine. Okay, so there, a very slight resonance on this thing. So we're at 4,000 right here. There's some resonance there, but that's not an XY angle, which this thing can cancel that. Okay, right here. Very slight resonance on this weird little angle there. That's not VFA that I'm seeing because it follows this, so it looks like this, and it follows this pattern here. So that is a resonance, which I could solve by just dropping my external acceleration to maybe 3,500. But I think it's fine for me. Yeah, in a bunch of these odd angles, you'll see them. There's more resonance there. Yeah, there's resonance here. So I'll just have to drop my external accels a bit. But if we go to a Voron cube, nothing there. Now this prints in X and Y, which is what your shaper is set up for. Is there something there? No. Whereas this prints in all the different angles. So my speeds could be off, my accelerations could be off for all these crazy angles. But on the standard square, it looks fine. What's the benchy look like? So we fixed the benchies. We put them up to 80%. Fix that. I'm looking here. And very, very slight. Nothing there. Okay, you can see some EM issues there. Right there. Probably need to tune its EM a little more for this filament. There's our smoothing that's going to happen. Our seam looks better. You slow it down a bit. So yeah, I I think that this is my go-to. I might drop this down to, let's say, 3750 maybe. Leave the internals at 4000. Drop that down to 3750. That'll give me my buffer. So by doing this exercise of comparing it, I've increased my print settings effectively. So if we look at my original, right, we were doing 125 perimeters, 100 infill. These were really slow. Accelerations were slow. Well, infill's at 5,000. I should probably infill's at 6 now. So I'm tuning it more and more. Still, my goal is always good prints over speed. And so if I can still get the good print at this updated speed, that's what I'm going to do. So this is kind of the data I used for comparing the Klipper. So all in all, what am I trying to say here? What I'm trying to say is, let's go back here. Oh, this is so horrible. Can we get rid of all this junk? In some situations, the damping ratio, we don't want that. The damping ratio won't matter. All right, Klipper's default of 0.1 is going to be good enough. However, if you have the opportunity and you have the chance, right, and it's a free program that Frick's made, use the updated shaper. It will get you. It may not get you more speed, but it'll give you a more accurate shaper, so that when you do push these limits of, Y is going to be our limiting factor, right? So if you're pushing 4,000, you might get less resonance than if you're pushing 4,100 at 0.1. I got to run that test. I didn't run that test. I got tired of printing cubes. But the damping ratio does matter. It does affect your shapers. Whether it's a big enough effect to have on the prints, that's going to be another run of tests for me. And this is something you guys can run yourselves. It's real easy. Just run a Voron cube and change the shapers midway. And tell me what you guys got, because I'm one guy with a day job. So tell me what you guys results of your test. Come hit me up on Voron Discord and say, look, I didn't notice a difference, or I did notice a difference in this situation. I will say that in the course of my own, once this damping ratio starts getting up to 0.8, right? So if a 0.8 to 0.08 to 0.1, it's becoming less and less of a difference, but 0.69 to 0.4, right, or 5, those matter. So I hope this helped you guys. I'm gonna leave all the information that I've used here from Klipper and Shaketune and all that stuff. I'm gonna leave it in the description. Do your own math. If you need the Excel sheet, you want it, just hit me up. I'll in Discord, and I'll feel free to send it to you. Any of these slides you guys want, just hit me up. I'll send it to you guys in Discord. But thanks for watching. Hope this wasn't too rambling and you guys got something out of it. Thank you for your time. Good night. Good morning.